Hey there, awesome viewers. Welcome to my video on variational autoencoders. I'm thrilled to have you here as we dive into the fascinating world of generative AI. Today, we're going to explore a really cool concept called variational autoencoders, or VAEs for short. Now, if you're new to the world of autoencoders, don't worry. I've got you covered. I actually have a previous post that breaks down the basics of autoencoders, so if you haven't checked that out yet, I highly recommend giving it a look. It'll give you a solid foundation for what we're about to discuss. In this video, we'll start by understanding the core components of VAEs, explore how the encoder network handles data compression, dive into the fascinating world of latent space and sampling techniques, and see how the decoder network generates new data. To wrap things up, I'll show you some practical applications and even walk you through a live demo. Trust me, by the end of this video, you'll have a whole new appreciation for these powerful neural networks. Let's get started. Before diving into the inner workings of a variational autoencoder, VAE, let's first understand its key components. On the left, we have the encoder network, responsible for processing input data and extracting essential features. The encoder produces two crucial parameters, mu and sigma, which describe the data distribution in probabilistic terms. These parameters guide us to the core of the VAE, the latent space, where data is compressed into a more compact, meaningful representation. Next, we encounter a sampling operation, which cleverly draws points from this distribution using the learned parameters. Finally, on the right, we have the decoder network, which reconstructs these sampled points back into the original data space, or even generates entirely new data. Now let's dive into detailed working of each components. Think of the encoder as our data compression expert. Unlike regular autoencoders, our VAE encoder does something really clever. It doesn't just compress your data by reducing the dimensionality of the data. Instead, it tries to learn the mean, mu, and variance, sigma, of the input data, capturing not just the features but also the uncertainty in the data. Think of mu as the sweet spot, where your data tends to hang out, and sigma as how much wiggle room it has around that spot. This probabilistic approach allows the VAE to represent data as a distribution rather than fixed points, making it more flexible and robust. By learning these parameters, the encoder essentially creates a blueprint for how the data is structured in a way that can be sampled and reconstructed later. Now that we have our mu and sigma defining the probabilistic representation of our data, the next step is where the real magic happens. Between the encoder and decoder, we introduce sampling step, where we use the mu and sigma parameters to draw samples from a normal distribution. This process creates a smooth and continuous latent space, a compact representation of our data that's perfect for both understanding and generating new data points. This smooth latent space is what makes VAEs so unique. Instead of mapping each input to a fixed point, as traditional autoencoders do, VAEs allow for some natural flexibility and uncertainty by representing data as distributions. This means that similar inputs will cluster closely together in latent space, while still allowing for slight variations. It's like giving the model a creative license to explore different possibilities while staying true to the underlying structure of the data. This probabilistic approach is what truly sets VAEs apart. By embracing uncertainty, they're not just reconstructing data, they're learning to understand its deeper patterns and relationships. And this understanding is what enables VAEs to generate entirely new data points that look realistic and meaningful. To make this probabilistic approach trainable end-to-end, we use a technique known as the reparameterization trick. This trick allows us to separate the stochastic and deterministic components of our model. Instead of directly sampling from the learned distribution parameterized by mean and sigma, which would break back propagation, we express the latent variable z as a function of both deterministic values and random noise. Specifically, z is computed as z equals mu plus sigma times epsilon, where epsilon is sampled from a standard normal distribution with mean 0 and sigma 1. By introducing this auxiliary random variable epsilon, the entire process becomes differentiable, allowing gradients to flow smoothly through the network during training. This step is crucial for making VAEs both powerful and practical, enabling them to capture complex data distributions while remaining fully trainable. Now, with a properly sampled latent vector z, the decoder network can use it to reconstruct or generate data that aligns with the original input's underlying patterns. Moving on to the final piece of our puzzle, the decoder network. Think of it as the creative artist of our VAE, breathing life back into the data. Once we have our sampled latent vector Z, the decoder steps in to transform it back into the original data space, reconstructing something that closely resembles our input. The decoder architecture mirrors the encoder, but in reverse. While the encoder compresses and extracts meaningful features, the decoder takes these compressed representations and expands them back into full-fledged data. What makes the decoder truly special is its ability to take the latent samples and reconstruct data that looks like our original input, preserving its key features. Learn a smooth mapping from the latent space back to the data space, ensuring that even slight variations in Z produce meaningful outputs. Generate entirely new, realistic samples by exploring different points in the latent space, unlocking its potential for creativity and imagination. In essence, the decoder is where all the hard work of encoding and sampling comes together to create something tangible, whether it's reconstructing what we already know or generating something completely new. Here's the cool part. What you're seeing in these block diagrams isn't just abstract theory. Under the hood, each component is actually a fully functioning neural network. The arrows represent connections between neurons, transferring information from one layer to another, while each block is a collection of multiple layers of neurons working in unison to learn and model complex transformations. Every parameter we've discussed, like mu, sigma, and z, are outputs of these networks, fine-tuned through training to capture the rich, underlying structure of the data. We've seen how these elements work together to compress data into a meaningful representation and reconstruct it with creative flexibility. Now, let's follow the fascinating journey of how a single data point transforms through the network. We'll start with the encoder network, which performs the crucial task of data compression. Let's take a practical example using the MNIST dataset of handwritten digits. Imagine we have a single handwritten digit 5 that we want to process with a VAE. This digit begins as a simple 28 by 28 pixel grayscale image, where each pixel holds a brightness value between 0 and 255. First, we flatten the 28 by 28 image into a one-dimensional vector with 784 dimensions. Next, we normalize the pixel values by dividing each one by 255, bringing them into a range between 0 and 1 for more efficient processing. This pre-processed vector is then passed through the encoder network, processing it through multiple neural layers to extract meaningful features. But instead of simply reducing the dimensionality like a traditional autoencoder, the encoder in a VAE takes a probabilistic approach. It doesn't just output a single compressed representation, it learns two critical parameters, mean mu and variance sigma. Think of the mean, mu, as the center or the most likely representation of the data in the latent space. It's where the data tends to cluster. Meanwhile, variance, sigma, represents the spread or uncertainty around that center. Together, these parameters define a probability distribution for the data in latent space rather than fixing it to a single point. By representing data as distributions instead of fixed points, VAEs can capture not only the features of the input but also its inherent variability. To summarize, the encoder network transforms high-dimensional input data into a compact, meaningful representation by learning its mean and variance. This process allows us to represent data in a way that embraces uncertainty while preserving its essential features. The output of this step is not just compressed data but a blueprint for how that data can be sampled and reconstructed. Now that we've seen how the encoder creates these probabilistic representations, it's time to explore what happens next. How do we use these mean and variance values to sample points in latent space? And how does this sampling enable us to reconstruct or even generate entirely new data? Now we know how encoder creates these probabilistic representations, let's explore how we use these mean and variance values to sample points in latent space, and how to make sampling process differentiate. Let's visualize our latent space in a 3D coordinate system. The mean vector we obtained from the encoder network represents the center point of our distribution. Think of this as the most likely location for our encoded data point. When we plot this vector, it gives us a specific position in our coordinate system. The variance vector tells us how much variation we allow around this mean point. This is crucial because it determines the spread of our possible samples. A larger variance means we'll allow more diversity in our generated samples. Look at the two bell-shaped curves along our axes. These are 1D Gaussian distributions, representing the probability of sampling points along each dimension. The peak of each curve corresponds to our mean values, while the width represents our variance. The higher the curve at any point, the more likely we are to sample from that region. When we extend this to 2D, we create a probability density surface. This surface combines the probabilities from both dimensions, creating a representation where the highest points indicate regions with the highest sampling probability, while the lower areas represent regions where sampling is less likely to occur. The gradual transitions between these areas show how the probability smoothly changes across the surface. Notice that our third axis isn't actually a spatial dimension, it shows the probability density. Points near the peak are more likely to be sampled, while points in the outer regions occur less frequently. This probability density interpretation is key to understanding how VAEs generate new data. When we sample points, we're more likely to get values from the higher density regions near our mean, but we can occasionally sample from the outer regions, allowing for controlled variation in our outputs. Now, let's sample a random point from this distribution. Watch as we generate a new point based on our learned parameters. This sampled point will serve as input for our decoder, allowing us to generate new, meaningful data that captures the essence of our original dataset. Now that we understand how sampling works in latent space, let's address a critical challenge: the non-differentiability of the sampling operation. When we sample points directly from a distribution, the randomness introduced by this process creates a problem. Specifically, random sampling is not differentiable, which means we cannot compute gradients through it. As a result, backpropagation, the core mechanism that allows neural networks to learn, cannot pass through the sampling step. This prevents us from training the network in an end-to-end manner, which is essential for optimizing both the encoder and decoder simultaneously. To solve this, we use a clever technique called the reparameterization trick. Instead of sampling directly from the distribution, we express our sampled point z as z equals mu plus sigma times e. Here, e is drawn from a standard normal distribution. By separating the randomness into e, which is independent of the network parameters, and keeping mu and sigma as deterministic outputs of the encoder, we make the sampling operation differentiable. This allows gradients to flow through mu and sigma, enabling backpropagation across the entire network. In simple words, reparameterization can be thought of as a clever way to handle randomness while keeping things smooth for learning. Instead of directly picking a random point from a distribution with mean mu and variance sigma, we first take a random number epsilon from a simpler, standard normal distribution, with mean 0 and variance 1. Then, we transform this point using the formula z equals mu plus sigma asterisk epsilon. Think of it as stretching and shifting the random point to match the desired shape of our distribution. This trick keeps the randomness separate from the learnable parameters mu and sigma, allowing us to compute gradients and train the entire model smoothly. To summarize, we've explored how the encoder creates probabilistic representations by learning the mean, mu, and variance, sigma, for latent variables. These parameters allow us to define a latent space that captures the essence of our input data. Sampling from this latent space involves generating a random point influenced by the mean and variance, enabling diversity while retaining meaningful patterns. The process is made differentiable through the reparameterization trick, which separates randomness from learnable parameters, ensuring smooth gradient flow and effective training of the entire model. Now that we've explored the latent space and how it captures meaningful representations of our data, it's time to dive into the next exciting step: data generation using the decoder network. The decoder is where the magic of creating new data truly happens. By selecting a point from the latent space, the decoder transforms it back into a full-fledged data sample, such as an image, that resembles the original data or even creates something entirely new. The process begins with a latent vector, which is a compact representation of the data obtained from the encoder in the previous stage. Think of it as a blueprint or a compressed code that encapsulates the essence of the data. Each dimension in this latent vector represents a meaningful attribute or variation of the data. For instance, in the context of handwritten digits, one coordinate might capture the thickness of the strokes, while another might represent the tilt or orientation of the digit. These latent variables form the foundation for generating diverse outputs. In this case I have kept only 2-dimension in latent vector, for visualization purpose. But practically, having more dimension in latent space, give V flexibility to capture different characteristics of the data. Next, this latent vector is passed through the decoder network. The decoder's job is to unravel the compact information in the latent vector and reconstruct it into a detailed and structured output. During this process, the decoder network applies a series of learned transformations, layer by layer, to generate data that aligns with the characteristics encoded in the latent vector. These transformations are guided by the training process, where the decoder learns how to map latent vectors back to realistic samples. The output from the decoder is an image array, essentially a long list of pixel intensity values ranging between 0 and 1. These values determine the brightness or darkness of each pixel in the image. The array is then reshaped into its original dimensions. For example, in the case of a handwritten digit, the output array is reshaped into a 28 by 28 pixel grid, representing the structure of the image. The latent vector might encode features like the overall curvature, line thickness, and orientation. As the decoder processes the vector, it reconstructs these features, and the resulting 28 by 28 grid closely resembles a handwritten 5. The process can be repeated with other points in the latent space to create entirely new samples which closely resembles input image. In summary, the decoder network takes abstract, compact representations from the latent space and transforms them into meaningful outputs. Whether reconstructing existing data or generating entirely new samples, the decoder demonstrates the power of neural networks in creative and generative applications. Now that we understand how variational autoencoders work, let's explore how our VAE organizes and interprets data in its latent space. We'll start by examining how individual images are encoded and gradually build up to seeing the complete structure of the latent space of trained variational autoencoder. Let's begin with our encoder network, which takes each input image and computes two key parameters: the mean, mu, and variance, sigma. These parameters define a probability distribution in our two-dimensional latent space. When we feed in our first MNIST digit, a handwritten 0, the encoder processes it and maps it as a probabilistic cloud rather than a single point. This cloud represents the uncertainty in the encoding, showing us that there isn't just one right way to represent this digit in the latent space. As we continue feeding more examples of the digit 0, each one gets mapped to its own probabilistic region, with these clouds starting to overlap. Watch how these individual distributions start clustering together. This isn't random, but rather shows how our VAE has learned to group similar images. After processing all 10 examples of 0, these overlapping distributions merge into a larger translucent circular region, representing the general territory where our VAE expects to find this digit class. This process repeats for each digit class, creating a beautiful diagonal pattern in our latent space. Notice how the classes naturally organize themselves. Zeros cluster at the bottom left, ones just above them, and so on, with 9s appearing in the top right. The slight overlaps between neighboring regions, shown by the translucent circles, indicate where digit classes share common features or variations in writing style. Now that we've visualized how our VAE organizes different digit classes in the latent space, let's explore something truly fascinating about the continuous nature of this learned representation. We can sample any point from this latent space and use our decoder to generate new digits. By moving our sampling point smoothly across different regions, we can observe how one digit gradually transforms into another. Watch as we place our sampling marker in the latent space and begin to move it. The decoder network takes these coordinates and generates the corresponding digit image in real time. As our marker travels between different class regions, you'll see smooth transitions between digits, not abrupt jumps, but gradual morphing of one digit's features into another. This demonstrates one of the most powerful aspects of VAEs. They don't just learn isolated categories, but create a continuous space where every point represents a meaningful digit variation, even in areas between known classes. These smooth transitions reveal how the VAE has learned to understand the underlying structure of handwritten digits, creating a rich, interconnected space of digit representations. This isn't just mathematical interpolation, it's the model's learned understanding of how digit features can smoothly flow from one form to another. Let me show you a small application I've developed that lets you explore this latent space interactively. This Python-based tool allows you to click anywhere in the latent space, and in real time, you'll see the decoder generate the corresponding digit. You can also drag your cursor to watch the smooth transitions between different digit forms. The application provides an intuitive way to understand how our VAE has organized and learned the structure of handwritten digits. As we wrap up our journey through the fascinating world of variational autoencoders, it's clear that these powerful neural networks are more than just data compression tools. They're gateways to understanding and generating complex data in ways that push the boundaries of machine learning. We've explored how VAEs compress data into a meaningful latent space, embracing uncertainty through probabilistic representations. We've seen how the clever reparameterization trick allows for smooth training, and how the decoder breathes life back into latent vectors, reconstructing familiar data or conjuring entirely new creations. Perhaps most excitingly, we've witnessed how VAEs organize data in their latent space, creating a continuous realm where digits smoothly morph from one to another, revealing deep insights into the structure of data. If you're eager to explore the mathematics behind variational autoencoders, I strongly recommend checking out the suggested video. If you prefer reading, visit my website where I've posted an article that thoroughly covers the mathematical concepts behind variational autoencoders. While you're there, feel free to explore other exciting projects I've been working on. If you enjoy my work and would like to see more content like this, please consider supporting me on Buy Me a Coffee. Your support helps me continue creating in-depth tutorials and articles on complex AI and machine learning topics. The link to support my work can be found in the description. Stay tuned for more content like this in the future. Thank you for watching.